This is lecture number 7 in this series on control systems 2. And so far we have done a number of examples on electrical circuits, state space models of various electrical circuits. And in the last session, we actually saw the state space model of a DC motor for a speed control system as well as for a position control system. Uh, today, we'll be looking at the analysis of a signal flow graph or representation of a signal flow graph in a state space form. So, what we have actually studied is we have derived the state variable model. So the equations that represent a state space model are x dot equal to ax plus bu. These are all equations in time domain. Y is equal to cx plus du. So if we were to represent these two equations using a log diagram method, we can say if you have a signal x dot, fine, x dot is summation of two signals. One is A times x and another signal is B times u, where u is the input of the system. And so you have x dot equal to ax plus bu. So where can we obtain this x from? X can be simply obtained by integration of x dot. So if we integrate x dot, we'll be getting x. If we integrate dx by dt, we'll be getting x. So we have x dot equal to ax plus bu. So this is your first equation. And your another equation is y is equal to cx plus du. So y is equal to, we already know this, we have obtained x. So this is y is equal to cx. And it is going to be, it's going to lie in cascade with d times u. So in case we have to represent these two equations using block diagrams, we have this representation where we'll be getting x dot equal to x plus bu and y will be equal to cx plus du. You have previously already studied the signal flow graphs, and if we were to represent this block diagram using a signal flow graph, we know that each summation point and pickup point can be replaced by a node. So if you have this as one node, you have this summer as another node. You can take this pickup point as another node and this summer as another node. So you'll be having actually 1, 2, 3, 4 nodes apart from the input and the output. So you have 1, 2, 3, 4, 5. So the output of this is actually y and the input of this is actually u. Fine. So at this point you can see actually we have pickup point, that's actually d. Fine. So the gain of this branch is actually d. Gain of this branch is b. Gain of this branch is 1 by s, and gain of this branch is c. You also have a point from this point to this point, the gain of which branch, the gain of this branch is actually a. So if we were to obtain a transfer function model of this particular signal flow graph, you can actually obtain ys by us by finding out the number of forward path gains and the number of loops gains in this system for this signal flow graph. So from the signal flow graph, we can obtain the transfer function of the system. We can obtain ys divided by us. Uh, we already know that the signal flow graph can be solved using the Mason's equation, and that's pi delta I divided by delta, where I is equal to 1 to n, where pi represents the gain of the ith forward path. I already studied this in control 1. Delta I represents delta of ith forward path, where delta is actually 1 minus summation of summation of all loop gains taken individually plus summation of loop summation of two non-touching taken two at a time. Summation of non-touching loop gains taken two at a time minus summation of three non-touching loop gains plus summation of four non-touching loop gains, and so on. Actually already studied this equation. So if we apply this equation here, the number of forward paths, how we can basically traverse from u to y without uh, without crossing the same node again. We can go from u to y via this path. We can go from u to y in this manner, or we can go from u to y in this manner, crossing the d, crossing through the branch which has the gain d. We can traverse the path u to y through two directions, and the gain of these two paths, therefore you have p1 equal to the uh, forward gain of path number 1, that will be b into 1 by s into c. That means basically b into 1 by s into c. Remember these a, b and c, they are matrices, so matrix algebra needs to be taken into account. bc is not equal to cb, and p2 is the forward gain of path number 2, that's actually d. Fine. And in a similar manner you will be having delta 1. Delta 1 will be 1 minus summation of all loop gains taken individually, so with for that are non-touching with this forward path. So with forward path number 1, there is no loop that's actually not touching with it. There's actually only one loop in this system, and that is this is your loop. With respect to with respect to path number 1, it's touching, so you cannot. So p1 delta 1 is only 1, fine. While as delta 2, that is 1, that is path number 2. The loop that's actually not touching with this is 1 by s into a. And as far as delta is concerned, uh, delta is 1 minus summation of all loop gains. As we know, there is only one loop gain. This is actually 1 minus 1 by s times a. It will be again 1 by s into a. So substituting these values in equation number 1, what we have obtained, ys by us is equal to p1 delta 1 plus p2 delta 2 divided by delta, where p1 is nothing but b into 1 by s into c. That means b into 1 by s into c. Let's keep it like this for a while. Into delta 1 is actually 1 into plus p2 is delta, and p2 is d, sorry, p2 is d, and delta 2 is 1 minus 1 by s times a divided by delta, that's 1 minus 1 by s times a. So if we were to find out this the transfer function from a state variable model, what we actually this what we are doing is we are actually trying to see the representation of state variable model in case of us through a signal flow graph. So we started with the state variable equations. We obtained the block diagram from those state variable models and converted that into a signal flow graph. Now we actually know uh, the how to solve a signal flow graph using Mason's gain formula. That's pi delta I by delta. So ys by us comes out to be b into 1 by s into c plus bd into 1 minus 1 by s times a divided by 1 minus 1 by s times a. Since these are matrices, so instead of writing 1 here, you cannot subtract 1 from another matrix. You'll be writing identity matrix here, I minus 1 by s times a. Fine. You can subtract a matrix from a matrix. You cannot subtract 1 from a matrix. You can subtract one matrix from another matrix. So instead of having 1 here, we'll be having I here. So this is b into c 1 by s. Since 1 by s is a constant term, we can take it out. B into c plus d into I will be actually d only, minus d into 1 by s times a. So you can say this is d into a divided by s. So since we have taken s out, this will be s times d, and this will be this 1 by s term here vanishes, divided by, again take 1 by s common here. Once you take 1 by s common here, this will become si minus a. Fine. So 1 by s and 1 by s cancels out. What you have here is bc plus sd minus da divided by si minus a. So if we take d common from here, this will be actually si minus a. We shouldn't have. This is bc plus d common si minus a divided by si minus a. That means this is si minus a, si minus a. So this and this cancels here. So ys by us is actually bc divided by si minus a plus d. Fine. So let's keep it like this for a while. We'll be actually deriving the transfer function model from the state space model mathematically. So this was we're actually focusing on the signal flow graph. So your state variable model can be converted into a signal flow graph easily, and you can have, this is actually a general representation of signal flow graphs, wherein we are having actually x dot, we actually represented x dot. So x dot can be a matrix Now, if we want to actually uh, represent all the state variables x1, x2, x3, we can do that also using the signal flow graphs. And if we solve the signal flow graph, we are getting ys equal to bc divided by s minus a plus d. Fine. We'll not consider this as the final equation yet, but you can actually use this equation for obtaining the transfer function from a state space model. So now let's take another example and try to see how we can represent this, uh, how we can represent a state space model now from a signal flow graph. Let's have an equation, have a signal flow graph like this. So let us assume we have a signal flow graph. This is our signal flow graph, and there are two terms, one by S and one by S. So that means there is an integrator in this signal flow graph model, signal flow graph, and if it means prior to the signal flow graph, there will have to be a derivative term. So if this is any variable, let's assume this is x1, uh, this is any variable x1, that means prior to the signal flow graph, we'll be having a term x1 dot. Similarly, if this is a variable x2, prior to this integrator, we'll be having a variable x2 dot. So simply we can write x1 dot is equal to minus 3 times x1 plus 1 times u, and x2 dot is nothing but minus 2 times x2 plus 2 times x1 first minus 2 times x2. So if in a signal flow graph you have an integrator, you can represent the variable after the integrator as x1 and before the integrator as x1 dot its derivative form. So this can be done for any signal flow graph, and in this case y is simply equal to x2. And when putting this in a state space model form, x1 dot x2 dot will be equal to minus 3 times x1 plus 0 times x2 and plus 1 times u. x2 dot is 2 times x1 minus 2 times x2 plus 0 times u, and y is equal to 0 1 times x1 x2 plus 0 times u. So this is your state space model from a signal flow graph. So in case of a signal flow graph that consists of an integrator term, after the integrator we can represent the variable as x1, x2s, the state variables, and their derivative form can be represented prior to the uh, their derivative form will be obtained prior to the integrator. So this example is fairly simple enough. Now, in case we have a signal flow graph like this, this b1, this b1 by s, this b1, and this b1 by s plus 1, this b4, and this is y. So in this case, as far as this first this term goes, this is an integrator. So if we represent this as x1, this will be x1 dot. But this is not 1 by s, this is 1 by s plus 1. We have to break it into a form that represents it as an integrator only 1 by s. So how to break 1 by s? Uh, so if we have a system, we have a system like this who's governed by equation that's governed by an equation 1 by s plus 1. We already know this can be represented as a unity feedback system like this. So 1 by s plus 1 can be represented as a unity feedback system wherein your forward path gain will be 1 by s and your feedback is unity, a negative feedback system rather. And this can then be represented as a signal flow graph wherein you will be having 1 by s as a forward path gain and minus 1 as the feedback gain. So this is this portion of the uh, signal flow graph can now be replaced by this signal flow graph representation. So signal flow graph changed the form and now we can represent it as you had 1 here, you had 1 by s here, you had minus 2 here, you had 1 here, you had 1 by s plus 1 here. Instead of 1 by s plus 1, we'll be having 1 by s and you'll be having a minus 1 in the feedback path. And you actually already had another uh, loop path that is represented by minus 5. And the gain of this forward path is 4. This is your y and this is your u. Now you can represent this as x1, this variable, such that this becomes x1 dot, and you can represent this as x2 such that this becomes x2 dot. And in this case now x1 dot can simply be written as summation of these the gains of these two branches, that is 1 times u and minus 2 times x1 minus 2 times x1 plus 1 times u. As far as x2 dot is concerned, it is 1 times x1 minus 1 times x2 minus 5 times x2, that is a total of minus 6 x2's, fine, and y is in this case equal to 4x. Therefore x1 dot x2 dot will be equal to minus 2x1 0x2 1u 1x1 minus 6x2 0u and y is equal to 0 4 x1 x2 plus 0 times u. Now we do not need to write that every time, 0 times u. So this is how we can obtain a state space model from a, from a we can obtain a signal flow graph from a state space model, and how we can obtain a state space model from a signal flow graph. Fine. Uh, Also, we have tried to derive the equation, tried to derive the transfer function. We'll actually be deriving that mathematically in the next session. So that's all for this session.